I won't start immediately. Get rid of this thing.
Hide video.
Hide it.
No. Maybe I'll just do that.
Yes.
Possibly.
Okay, thanks. Our next speaker is Adam Topaz. We'll be talking about formalizing Lawvere theories and dependent type theory.
Thanks. Yeah, thanks for the introduction. The talk that I'm gonna give is gonna be very different from both the other talks today and the usual math talk, because I'm gonna talk primarily about formal verification of mathematics and formalizing mathematical definitions and objects. So the actual math itself is kind of very classical and well understood. There's not going to be pretty much any new mathematics. What this talk is really about is encoding this piece of mathematics in this formal system based on dependent type theory. Okay. So to start off, I was planning to give a brief demo of what it feels like to formalize mathematical definitions in this dependent type theory. Dependent type theory, it's a different foundation as opposed to set theory. I'm not going to give you the definition of what dependent type theory is. If you're interested, look it up somewhere. The jargon is that it's the internal language of a topos. If that makes sense to you, that's fine. If not, that's fine as well. But I hope that with this demo, it'll give you some feel for what it feels like to actually do this concretely in a proof assistant, which this is. So this is a VS Code window, and it's running the Lean4 interactive proof assistant, okay? There are two sides to the window here. There's this side, which is where I'm going to write the code. And then there's this side, which is called the info view, which is going to give me feedback about what I'm actually writing, okay? And it's going to be updated in real time as I write the code. Now, Lawvere theories, which is the main thing I'm going to talk about, it's a categorical way of doing universal algebra. So to start off, let's just talk about some algebra, okay? So let's define monoids in Lean, right? Whenever you're formalizing something, you have to make design decisions. I'm going to give you the definition of a monoid as it exists in the mathematical library of Lean. There are other approaches, which I'll maybe briefly touch on, but let's just get started. So what is a monoid? Well, it's a type. So I said this is based on dependent type theory. For our purposes, when I write type, you can think of that as the collection of sets. Okay. So here I'm saying that M is a term of the type of types. In other words, M is a type. Right. Now a monoid is an algebraic structure with a multiplication and a 1, right? So I need to have a multiplication. And the multiplication here takes two elements of M and gives you back an element of M. Now, I was talking with Jim earlier today and got confused by this notation. Think of this in terms of lambda calculus, okay? So this is the type of functions whose input is M and whose output is the type of functions from M to M. So for every input in M, I get a function from M to M, which I then can put in another input and get a value of M. Okay? So mol is supposed to be a term of this type. And then 1 is an element of M. Right? And then I have the usual axioms. So if I multiply 1 by some arbitrary element x, I should get x. Okay? In other words, 1 times x is x. The notation is a bit strange because we haven't defined notation yet to write 1 times x, all right, but I'll do that in a moment. The other obvious axiom, and then associativity. Also, so if I have 3 elements of M, and I multiply the product of x and y with z, that should be the same as multiplying x with the product of y and z. Okay? I hope this makes sense to everybody. All right, it's just the usual definition of a monoid. Just encoded as a structure which has a binary function, a zero array function, if you wish, and then 3 axioms. Okay. Let me hover over this for a moment so we can see what Lean has understood from my writing. It has understood that the field of the structure called monoid, whose name is 1 mole, has this signature. It takes a type, an instance of this class that I've just defined, an input x and m, and that is a term of the proposition that the product of 1 and x is x. Okay? That's what it means. Now, I said that we can introduce notation. Let me just briefly do that so that we don't have to keep writing mole xy. So if I have a monoid M, then I should have a multiplication on M, where mole is monoid mole. This is not so interesting. This is just so that I can write notation. And then I'll be able to write, for instance, expressions as we usually like to write. With the usual multiplicative notation 1, instead of having to write mole all the time. Okay? Okay, this is just the definition of a monoid, not very interesting, because when we want to do algebra, we want to relate different monoids. Okay, so we want to be able to talk about morphisms. We want to be able to talk about sub-objects. Okay, we want to be able to talk about quotients. Okay, all of these kind of standard algebraic constructions. I'm not going to go through everything. Obviously, we don't have time for that. Let me just explain how morphisms work, and then I'll move on.
Can I ask you a question? Like,
Yeah.
why does it say sorry?
Oh, because this is false in general, and sorry is it's like a placeholder. So sorry is a keyword here that can fill in a term for any type. So with respect to the Curry-Howard correspondence, which is how you prove theorems in the system, propositions are types, and a term of the type associated to a proposition is a proof of that proposition. So maybe I should give you an example that's actually doable. So if I have, say, 1 plus x, so this should be, let me say here that I also have a proof that x times y equals y times x. Then, okay, so this is now a true theorem. Okay, if x times y is y times x, and I'm working in a monoid, then this is going to be true. Okay, but I wasn't planning on doing many proofs, but because Jim asked, let's prove it. So when I write by, I enter what's called tactic mode, and the info view changes. Okay, so here's the goal that I have to prove, and here's my context. All right, and tactics, all they do is they are somehow programs, they're scripts in some sense, that construct terms. Okay, so it's a scripting language, and so it's a language that lets you iteratively construct a term. This is the term I'm trying to construct, and these are the hypotheses that I have available. So what's the first step here? Remember that here I'm multiplying y and 1 first, okay? And then I multiply the result by x, right? So the first thing I could do is I could use this axiom mol1 to replace y times 1 with y. Okay, so let me rewrite with mol1. Sorry, demo. No, what? Okay, sorry. Well, now I have egg on my face. Okay, this is kind of annoying. Why is this?
I think you're proving the point. It's hard to do a formal proof.
It's hard to do. There's the proof. It's hard.
It's not a formal proof that that's true, but.
Come on. Okay. So that works. Okay. Okay. So instead of rewriting with mol1 first, I rewrote the right-hand side using my hypothesis. And then I'm going to use congruence. Okay. And then I hope I should be able to apply monoid 1. So there we go. There's a proof. Z was not needed. Great. All right. A very basic example of a proof. Not anything groundbreaking. Yeah? My point in this talk is not to talk about how to prove things. During the talk I'll give tomorrow, if people do come, I'll say more about how tactics work and things like this. For today, I want to focus more about defining things. Right? So like I said, let's talk about how to define morphisms. So let's say monoid morphism. So this is going to take 2 monoids as an input. And giving back a structure which has a function between their underlying sets. Okay. That's supposed to be compatible with multiplication in 1. So let's say map mol okay, compatible with multiplication and compatible with 1. Okay, pretty straightforward. Let me give one more example of a kind of structure you can define in this context, namely the notion of a subobject. So I guess I call it a submonoid. So what is a submonoid? Well, I need to give a subset of M, which is closed under multiplication and contains 1. In dependent type theory, at least in Lean's dependent type theory, the way we talk about subsets is via their predicate. Okay, the predicate that says that an element is in a subset if and only if it's in the subset. Yeah. And this set here is the type of subsets of M. And let me just briefly flash how it's, why is this not working? So here's how it's defined. Okay. The type of subsets of a type alpha is defined as predicates on alpha. It's a function that takes an element of alpha and gives you a proposition. Okay. So in the system, we literally define sets, subsets, as their associated predicate. Okay. It should contain 1. And it should be closed under multiplication. Okay. So now, because I have a subset, I have to talk about it as if it's a predicate. And to get the proposition that says that an element is in that subset, I use the member of notation. Okay. So this is just saying that the carrier subset is multiplicatively closed. If I have two terms of M, both of which are in the carrier, then their product should also be in the carrier. Okay. Very natural so far. Okay. So far so good. I can keep going. We can talk about quotients, for example, but if you've ever tried to teach undergraduates about quotients of monoids, you realize that it's actually a non-trivial thing. Because you can't just talk about analogs of normal subgroups, right? So I'm not going to do that. We could do it, but I'm not going to do it. What I want to talk about rather is the more categorical notions associated to an algebraic object of this sort. So the first thing we can do is talk about the category of monoids. I've defined morphisms, but how do we package that into some convenient container that works like a category? Well, the way categories work, at least in Lean's mathematical library, is that the collection of objects is a type. Okay. And then to every two terms of that type, you associate another type of morphisms between those two objects. Right? So the very first thing I need to do is define the type of monoids. Now, what I've defined here is not the type of monoids. This is the structure of a monoid on a particular type M. Right? It's literally a function. If I look at the signature of monoid, so let's check monoid here. Right? If I look at its signature, it's literally a function that takes a type as an input and gives you a type as an output. What I want is to bundle this M into the structure in order to talk about the type of all monoids. Right? So that's what I'll do. Oops. Now you saw my cheat sheet at the bottom. Okay. So let's talk about a bundled monoid. Well, there's a carrier type. And the structure of a monoid on it. Okay, pretty straightforward. Right? Okay. Now, there's an issue. If I have two bundled monoids, I want to be able to talk about morphisms between them in the sense of morphisms of monoids that I've just defined above. But if I just try to write A, B here, I'll get an error. Why is the error appearing? Well, this is a type checking error. And this is what formal verification is. This is what it means for the computer to verify your mathematics. It checks that the types and terms make sense. Here, I gave Lean a term A of the type of bundled monoids, but it expected A to be a type with the monoid structure separately. Okay? Similarly for B, but it complained about the first error that it saw, namely A. I could write A dot carrier, which is a type. Okay? But then there's another error that Lean doesn't understand how to think about the monoid structure on A dot carrier because it didn't tell it what that structure was. This is just some boilerplate that is quite easy to fix. Let me just quickly fix it. So this tells Lean, well, whenever you see a term of bundled monoid, automatic, and you expect a type, coerce it using the carrier. That's all this is saying. So that will let me get rid of the dot carrier in the syntax here. But then it still doesn't know the monoid structure, but I can tell it what that monoid structure is. So if I have a bundled monoid, it's going to be a monoid. And then the error went away. Okay? So this is just some engineering work in some sense, but when you're just building up the algebraic hierarchy in the system, this is the kind of stuff that you have to do. Okay, so let me move on to the category side of things. So let's talk about the category of monoid, category of bundled monoids. So let me open category theory. Okay, so let's see what I have to provide a category structure. And here's where the info view is going to come into, is going to help me out. Okay. So I'm defining a category structure on the type of bundled monoids, which means that the terms of this type should be considered as the objects of the category. So I have to provide the notion of a morphism, right? What is a morphism? What is the type of morphisms? Well, it takes two bundled monoids and gives you back the type. Okay. I know what to do here. Namely, it takes X and Y and gives you morphisms from X to Y. Okay. Then I have to provide the notion of the identity map between monoids. So if I have a monoid X, I have to provide the identity morphism, which is just the identity function under the hood. Okay. Now, because this is the identity function, the proof that it's compatible with multiplication and with one is by reflexivity. So there wasn't much of a proof there. For composition, I would have to do something similar. I have to tell you how to compose two morphisms. Okay, I'm going to stop going through all this kind of triviality quite soon. So here, this is G2 fun composed with F2 fun. Okay, I could prove this by map mol. Okay, so the simp is an example of a tactic. I'm not going to go through what it actually does today. I may say something about it tomorrow. But if you're familiar with rewriting systems, this is an example of a rewriting system that lets you rewrite expressions with certain lemmas, like the lemma f map mol that says that f is compatible with multiplication. Okay. And then let me, okay, and then we have to prove the three axioms of a category, that composing with identity on either side doesn't do anything, and that it's associative. Lean is nice in that it has some good automation that will fill in trivialities like this automatically. So in fact, I can just omit those fields altogether and the automation takes care of it for me. All right? Okay. So that's the category. Let me show you how to define a functor. So the forgetful functor. Oops. Oops. Okay, so a functor is a function on objects, a function on morphisms that's compatible with the categorical structure. The forgetful functor for monoids just sends a monoid to the underlying type. It sends a morphism to the underlying function. And the automation gives me the other two lemmas for free. Well, not for free, with some automation, okay? Now, this is where I'm gonna stop defining things, because the next thing I wanna talk about is the fact that this functor has a left adjoint. In other words, the functor that takes a type and gives you the free monoid on that type. Okay? So that is a functor called free from type to bundled monoid. And I'm going to leave that as a sorry, meaning that this is in a book, you may read this is left as an exercise to the reader. Yeah? Okay? So like I said before, sorry is a placeholder that can fill in any term. So here I'm telling Lean, well, you should expect a term called free, whose type is the type of functors from the category of types to the category of bundled monoids. And I'm too lazy to fill in this term right now, so I'm just going to leave it as a sorry for later. Okay? Or as an exercise to the reader. There's also an adjunction that free is a left adjoint to forget. And of course, I haven't defined what free was, so I can't tell you what the adjunction is. Okay? Okay. So far, this is kind of standard algebra. Now, as soon as you get beyond undergraduate algebra, and you enter maybe graduate algebra, you want to talk about things like algebraic groups, or group schemes, or Lie groups. You know, what are these kind, or Lie monoids, if you want. What are these kinds of objects? They are internal objects in a certain category, right? Lie groups are groups internal to the category of smooth manifolds, for example. Group schemes are group objects in the category of schemes. Okay. So let me very briefly explain how to talk about internal objects in the system. Okay. Okay, structure, internal object. Now, I have to tell Lean where that internal object should live. In other words, I have to provide a category with suitable products so that I can define the analog of the operations and so on. So I have to provide Lean with a category C. And I want products in this category so that I can write, for example, the multiplication operation as a morphism in the category from the product of m with itself to m, right? That's what the multiplication should be. There are various ways of talking about products. I'm going to use something that's in this project called chosen finite products. The notation coming out of this is going to look a bit different. What's going on here is that this tells Lean that C should have some notion of binary products in a terminal object in the category, but in some concrete sense. It turns out that the actual library has a different way of talking about products and terminal objects that's not computable, but in this sense, I want it to be computable. So the way I've arranged for this is to view such a category as a monoidal category, where the tensor product is the product in the category, and the unit in the monoidal category is the terminal object. So the notation that you'll see in a moment comes from the monoidal category side of things, but the monoidal structure is just the Cartesian structure. Okay. So multiplication here, well, first I need a carrier, right? An object of C. Multiplication is a morphism. Oops. I need to open monoidal category. Okay. Multiplication is a morphism from the carrier times itself to the carrier. The 1 is a morphism from the unit of the tensor to the carrier. Okay. And now I have to write down the axioms. Okay. So the axiom mol1, the categorical analog. So mol1 said that for any x, x times 1 is x. So how would I phrase this categorically? Well, here I have one input called x and some equation. Okay, I want to represent this equation as an equality between two morphisms in the category. And because I have one input, both the input and the output of that morphism should be the carrier. Let me call the carrier M for simplicity. So I want M, okay, to M. And I want two morphisms, one representing X and one representing X times 1. So how would I represent X? Well, that's just going to be the identity. The identity morphism. Because it takes every element X to itself. Okay. How would I represent X times 1? Well, I first have to map M to the product with the unit. Okay. And then I have to, let me do it like this. And then I have the multiplication mu. But then the question is, what is this map? Well, this is the map that should send X to X1. Right? And this is the multiplication. So let me just briefly show you how to do this. I'm not going to spend too much time because I want to get to the other parts of this talk. Mol1. So I'm first going to lift the identity on carrier with 1, and then compose with mol. You know what? For the sake of time, let me just copy from my cheat sheet here. Okay. And I need to open a chosen products. Okay. I don't have time to really go into what's going on here, but this is the categorical representation of the two axioms. And I did not have the associativity prepared, and I don't have time to write it down. So let me just leave that as a sorry. Okay. Fine. That is, roughly speaking, what an internal object is. I hope you're all bored at this point, because I certainly am. My point being is that all of this should have been done for me automatically, right? This is all complete boilerplate, right? As a mathematician, I don't want to have to do all this every time I want to define a new algebraic structure. The question is, how do I solve this kind of engineering problem that, starting with a class of monoids, as I defined up here, how do I automatically generate all of this boilerplate? Okay. Now, I should say that the way that things are currently done is that some human has to actually write all this code in the library for each algebraic structure that they want to talk about. The hope is that in the future, this is not going to be the case. So this brings me to the notion of a Lawvere theory. A Lawvere theory, as I said before, is a categorical way of talking about universal algebra. And the reason that I want to use Lawvere theories as opposed to structures and theories in the sense of model theory is because of these last kind of few examples involving categorical objects, right? There is no notion of an internal field in a category with products because there is no way to categorically represent the fact that every non-zero element has an inverse. What I can do is represent an internal ring. Okay? In other words, I can represent structures that come from universal algebra, but not structures that come from model theory. So that's the first observation. The second observation is that, well, universal algebra just deals with sets, and I want to deal with a more general construction that I can easily represent in an arbitrary category with products. And that's what Lawvere theory is. Let me give you the definition, because I don't think this is something standard in a logician's education. So here's what a Lawvere theory is. Definition. So let me first give you the single sorted definition, and then I'll tell you what the multi-sorted definition is. So a Lawvere theory, single sorted, is the structure of a category on the natural numbers. Now, the natural numbers contain zero, okay? Where addition of natural numbers corresponds to the categorical product. So, A plus B is A times B. What do I mean by this? This is the sum of natural numbers in the natural number sense, and this is the product of the objects in this category. Okay? That's it. That's the definition. How do I interpret this in terms of algebra? By the way, when do I have to stop? 55, right? Yep. So how do I interpret this in how do I, like if I have a Lawvere theory that's supposed to correspond to monoids, how do I define the notion of a monoid out of this? Well, that's the concept of an algebra. An algebra of a Lawvere theory, L, is a functor L, it's in category C, which preserves products. Okay. So what's the idea? So yeah, just a second. What's the idea? The idea, think about C as being like the category of sets. If I look at the image of 1, that'll give me a set, right? And that is the underlying set of the model in some sense. Morphisms from 2 to 1, each will give me a morphism from that set squared to that set, which is the collection of binary operations in this theory, in this language. Okay? You got a question, Jim?
No, oh, no, sorry. You answered it.
Okay, yeah. So again, because this preserves products, and because 0 is the terminal object, and every other element is a categorical product of 1, this is completely determined by where 1 goes on the level of objects. Okay, so if I call this F, then it has the property that Fn is F1 to the n. Okay? So that means that I can think about functions or operations on this set F of 1 coming from the category structure on this natural number set, on the natural numbers. That's the single sorted story. There's also a multi-sorted story, which you may imagine what happens. Essentially, instead of taking the natural numbers, think about the natural numbers as being the type of lists on a single element set. So, and that single element is the single sort. So instead of taking the natural numbers, if I have a set of sorts S, I would take lists on S where concatenation of two lists is the product. Okay, that's a multi-sorted Lawvere theory. And then the same definition works for the algebra side. Except now I have multiple sorts, one associated to each element of S. Okay. That's the abstract categorical, very slick definition. In practice, of course, that's hard to work with. It's not completely clear how I would take this notion of a monoid and construct out of this a Lawvere theory. Okay. Well, it turns out that it can be done. There is the notion of generators and relations for a Lawvere theory. Okay. So just like groups can have presentations, Lawvere theories can have presentations. If I specify that I should have some Lawvere theory which has a multiplication map, which is a morphism from 2 to 1, and a 1, which is a morphism from 0 to 1, subject to some axioms, I can freely generate the Lawvere theory with those generators and relations. Okay. For the sake of time, I'm not going to give the precise definition. And in the last 2 minutes, let me briefly give a demo of what can be done. So let me delete all this nonsense. And let me verify this class. What that does is it will automatically generate a Lawvere presentation, a presentation for a Lawvere theory. It'll automatically generate the Lawvere theory associated to that presentation and the notion of an internal object in a category associated to this class. So monoid dot Lawvere, so internal object, okay, is the notion of an internal object automatically generated out of this class. Now, this is still work in progress. This is very early days in this kind of automation that I've made. I've constructed this category of internal objects. And what has not yet been done is this last observation that the internal objects to the category of types do all have instances of the original class. That's somehow the last step that is yet to be done. But pretty much all the other constructions that I've talked about, all the boring constructions that I bored you for the first 30 minutes, are in some sense automatically generated pretty much directly from the definition. Okay, I'm pretty much out of time, so I'll stop here. Thanks.
So like there's a fundamental theorem of groups. Is there a fundamental theorem of Lawvere theories? I mean,
What is the fundamental theorem of groups?
Isomorphic image.
Like the first isomorphism theorem.
Yeah.
Yeah, there's a first isomorphism theorem for algebras.
Second and a third too, right?
Yeah, that's right.
And you're gonna try to implement all of them?
Yeah, but the point is that you can implement them just on the categorical side.
And so I must admit that I learned algebra, my algebra teacher did universal algebra.
Yeah.
And I didn't learn anything the first year. So I had to redo it all when I actually did it more concretely.
Yeah.
So do you think learning that is going to be helpful? I mean,
No.
I mean, I agree with you.
But that's my whole point. My whole point is that it's not useful, but the automation will do it for you.
Yeah, but then you don't, I don't think you know it. You might learn it, you can prove it, but you don't know what it is until you play with it a little bit.
Okay. This is something for building libraries of formalized mathematics. This is not something to teach undergraduates how to work inside of a monoid. I agree.
I'll stop there.
Other questions?
So you said, like, you can think of your theory, like, as some kind of generalization of a set with operations on it like that. So then, what about like, proving kind of, I don't know, very general things like similar to what was discussed in the previous talk, like, for instance, can you characterize like when you can embed a given finitely generated Lawvere
That I
theory?
have no clue. Yeah.
Like in terms of recursion theory on
I don't think that's,
on the
I don't think that's something that generalizes to arbitrary algebras for arbitrary Lawvere theories.
No.
I don't think so. Like for example,
What
the
was this
question,
called? This was called like Hickman's theorem or something. Well, we should ask Isabel, but yeah.
yeah, maybe you know.
This is a question like, if you have like a like computably presentable algebra in general, does it embed into a finitely presentable? I don't think that's always true.
I don't think that's, yeah, I think that's special, right?
Don't you have an example with semi-groups where this doesn't work? Oh, okay, I'm thinking of something else. But I think that's that's not true for every.
Really?
Yeah.
What is it about groups that makes it work? I mean,
The proof goes through, like, there is a lot of HTML extensions. I don't know the details.
I mean-
They show that groups can encode Turing machines.
okay.
Like you need to have all sorts of groups.
I mean, look, a much more stupid example of something that fails is that like quotients don't work in general in the same way as they do in groups and rings.
Yeah, sure.
Which is why the fundamental theorems are very difficult to understand.
You're right. You have to talk about congruence relations and things like that.
I mean, that's the first thing you do with groups is you do the fundamental theorems, right? And then
Yes.
you already get in trouble when you do it this way, right?
Yes.
So you don't even go any further. That's my feeling.
Okay.
Done without that.
Oh,
Oh, that wasn't for you.
Oh, there's chats.
It was from Isabel Scott.
Any questions? Matt, let's thank Adam. 5 minutes.